Hey everybody, in this video we are going to look at how the eye works and how we can model it as a single positive lens, and then talk about some common vision problems and how we might be able to correct those with prescriptive lenses, or prescription lenses I should say. Okay, so I'm going to go to our home page, our course page, and I just want to show you where I'm getting this picture. It's right here. Look at parts of the eye. So there's the eye. It might be hard to tell, but the way this is oriented, the light's coming from the left traveling to the right. So imagine there's light coming from an object, and the first thing that the light's going to hit is the cornea, which is right here, that transparent tissue. Now the cornea has some curvature to it. It will refract the light. In fact, most of the refraction of the light of the eye is done by the cornea. So the rays will get refracted. They'll enter the aqueous humor, which is this watery stuff right here. Then they'll go through the opening of your iris. That opening is called the pupil. So your iris, that's what's blue or brown or hazel, right? And then that black circle that you see in your eye, that's actually a hole, an opening. That's the pupil. The iris can change the diameter of that pupil depending on the light levels. So if it's a lot of light, it'll make the pupil have a smaller diameter. As the light level reduces, the pupil opens up and increases its diameter. The light that makes it through the pupil will then hit the lens of the eye. We call it just the lens. I think it used to be called the crystalline lens, but I'm not sure why, because it is not made out of crystal. It's a tissue. The light is then refracted by the eye lens, and then if everything works right, it travels through this vitreous humor, this jelly-like substance, and forms a focused image on the retina, on the back of your eye here. Okay? On the retina, you have your photoreceptors, the photosensitive cells, rods and cones. They're called rods and cones because they're shaped like rods and cones. You have, I forget the exact number, but millions of these on your retina. You have fewer cones than rods. The cones have a really strong frequency response, so they can distinguish colors and shades of color very well. They do need, though, a higher light intensity to work. The rods, which you have more of, they don't distinguish colors as well, or shades of colors, frequencies, but they will work in lower light levels. You may have noticed at dusk, for instance, colors appear to be washed out a little bit, maybe not as vibrant, and shades of a particular color, like maybe shades of red, are harder to distinguish when you're using your rods exclusively and not your cones. Okay, once the light hits the rods and cones, generates an electrical signal, right? That electrical signal then travels through the optic nerve, down along the optic nerve, I should say, into your brain, and you see. Where the optic nerve comes in and attaches to the retina here, you have some blood vessels here also. You don't have photoreceptors right there, so the part of an image that's formed right there at that spot, you won't see that part of the image. That's the blind spot. We're usually not aware of that because the blind spot is that spot where the optic nerve comes in is not right on the central axis. It's down to one side. So it's really it's parts of the object that are in the periphery. That part of the object will get imaged onto your blind spot. So you're usually not aware of it. You can see it. What I should say is you can find the blind spot in your vision. But what you have to do is you stare at, well, I can show you in class. It's sort of a fun thing to do. It's a little bit hard to do because you have to keep your eyes straight ahead and have somebody move an object around in your periphery. And at some point, you'll see that vanish. Okay, anyway, I digress. Okay, now, I mentioned that we can treat this system of the cornea and the eye lens as really just one positive lens that does all the refracting. And in that model, I want to think of the thin lens equation, 1 over f equals 1 over p plus 1 over q. The image distance q is pretty much fixed, right? The distance from the cornea lens, right, that combination, that distance from a midpoint, let's say, to your retina, that distance is fixed. It's typically a couple centimeters. Now, p in that equation, the object distance, that changes all the time, right? You can focus on something that's far away. There's a tree far away. You can see it. Or if you look at your watch, which is right now, p is really small compared to what it was, you can see that just fine too. So the object distance changes. Q is fixed. According to the thin lens equation, the only way that works is if the focal length of the system is changing. And it does. It's quite remarkable. The way your eye does that is it actually changes the shape of the lens, the eye lens. This is a pliable tissue. The ciliary muscle is attached to that lens. So in the relaxed state, that lens is as less curved as it will be. And that means it has the longest focal length. But if you need to look at something that's closer to you, where P decreases, you have to get the focal length F of the system to decrease. So your ciliary muscle contracts, and it'll actually squash that lens, make it more curved, and shorten the focal length. And it happens almost immediately. It's quite remarkable. It's known as the accommodation of the eye. Okay? All right. I have another picture that shows the photo response of the eye. I don't know if it's worth showing this to you or not. We've mentioned this before. I'll go ahead and show it to you. It's on the same line here. Might be hard to see, but there it is right there. It probably is hard to read. This is photocopied from an old book on vision. On the vertical axis is just the luminous efficiency, which is just the normalized quantity. It doesn't have units. The higher the number, the better the response of your eyes, of your photoreceptors. On the horizontal axis is wavelength, free space wavelength. So it goes from 400 here, nanometers in the violet, to 700 nanometers up here in the red. And you can see, if you look at what's called photopic vision, that's where your cones are dominating the visual response. You can see that it's a very non-uniform response, and your cones are most sensitive to wavelengths, free space wavelengths, right near the yellow-green, 560 nanometers. Your cones have your rods have a similar curve, but their peak is shifted down a little bit. Okay? All right, we mentioned that again when we were talking about the spectrum. Okay, so what I'd like to do next is go to the summary notes so we can look at some vision problems and how to correct those. And the first problem I want to talk about is myopia, which means you cannot see things well far away. So that's sometimes called nearsightedness. I find that really confusing, but you can't see things well far away. They're blurry. So if you're wearing glasses to drive or see the board, right, like I do, you have myopia. All right, so what's the problem there? Well, the physical problem is that if you're looking at something far away, as the light rays come into your eye, the cornea and the eye lens, they're actually refracting these rays too quickly. The image is being formed before it gets a chance to hit the retina. So the image is formed before the retina, and then the light spreads out, and once it hits the retina, you get a blurry image. It's not in focus. So I can try to draw that. Oh my goodness, let me see what I can do. Okay, so it would look something like this. If I were to draw this as a simple system, a simple optical system. Sorry, let me, there we go. So here's my optical, or my optic axis. Oh, hello. I'm having technical, there we go. Technical difficulties. No, that doesn't want to work. Oh, haha. Yes, everybody, once again, my pad is off. All right, very funny. Now it should work. Here we go. Let me see if I can draw. Yes, there's an optic axis. So I'm going to represent your eye with this positive lens. Now I'm not going to do an official ray trace because that would be too difficult for me to do it well enough. Okay, but basically what's happening is if you have an object that's out here, let's say your retina is right here. So you would love the image arrow. It's going to be a real image arrow inverted to be formed right there, but what's happening is it's being formed right here. So if I were to trace a ray, and I'll try to do this. Okay, so it will look something like this. This ray, as it comes in, right, from here, it's going through this focal point, and then it's forming the image point right here, okay? So, see, you really have, for the distance between your eye lens and your retina, you have too short of a focal length. It's like there's too much curvature to the relaxed lens in your eye, or there's too much curvature on your cornea. In fact, that's why if you have myopia, and this happens a lot when you're growing, like in middle school, because as you're growing, right, the proportions may not be right. The distance between the lens in your eye and the retina may not fit the curvature of the cornea and the lens in its relaxed state. So what do you do before you get glasses? You do a lot of squinting. What you're doing there is it's counterintuitive, but by squinting, you're actually flattening, getting less curvature on the lens. So the solution is, what you do in terms of this picture is you stick, you stick a negative lens in front of your cornea. So you would come over here and you would stick in. Now the negative lens will actually be like this, thinner in the middle. So what'll happen is when this red ray comes in, it'll actually be diverged a little bit like that. So now the system of your cornea and your lens will focus this. Oh my goodness, let's see. See, I have a little bit longer focal length, and it'll, whoops, I need to go here, right there. And it'll form the arrow right there. I didn't do that perfectly, but you get a longer focal length. Okay? All right, now, there's an easier mathematical way to figure this out. So I want you to think of the thin lens equation. Okay, before we get to that, we have to establish what we mean by the far point. And again, this is for myopia. So what's the far point? I'll call it the F dot P dot. Well, we've heard about the near point, which is what's the closest an object can be to your eye and you can still focus on it. And the healthy near point we said is 25 centimeters. The far point is what's the farthest something can be from your eye and you can still see it clearly. Okay, so think about that. Think about if you have a healthy eye, not one that has myopia. What's the farthest distance you can have for an object and you can still see it clearly? Well, it's going to be pretty big. In fact, if you think about it, think of a star. Don't look at our star, the sun, okay? Don't do that, that's not good. But at night, you can go and look at some other star. Now, I know they're really far away, so all you're going to see is this tiny dot, but the dot's in focus if you have a healthy eye. So really, the healthy far point, it's really big. In fact, we can say it's approximately infinity. So if that's the case, what we can do is design the lens as such. If you have a myopic eye, you're going to have a far point that is much less than infinity. It might be a meter or so, right? Or a couple meters. So here's what we do. When something is really far away from your eye, right? So here's your eye over here. When something is really far away, right? Approximately infinitely far away, we want the image formed by the negative lens that we're going to stick in front of your eye. Here's that negative lens. There's a little bit of curvature there, but oh my gosh. Meh. Let's try that again. Here's your eye. Here's my negative lens. A little bit of curvature and then a lot of curvature. That's okay. Not much better. But look, here is where the object is really far away. What we want this to do is to form an image, a virtual image, that is at the eye's unhealthy far point. Right? Because look, let me go back to the ray trace. Let me do that. If I go back to this ray trace that we did for the negative lens, can you guys see that? Okay, remember the negative lens gives us a virtual image right here. So when the object is really far away, we want this virtual image to be at the unhealthy far point of the eye. So if the far point of this myopic eye is 2 meters, let's say, you can't see anything beyond 2 meters. When you're looking at something really far away, we want that to be, the image to be formed at your far point. So that every object that's closer than this will get formed, the image will get formed closer than this image. Okay? So that's how we design our lens. So what we can do is we can say, okay, if we go to the thin lens equation, if I have 1 over f is equal to 1 over p plus 1 over q, what we say is, okay, look, we let p be really big. We let p go to infinity. The object's really far away, so this is 0. We want q to be negative. It's negative because it's a virtual image formed on the left side. Negative the far point of the myopic eye. So again, if your far point is 2 meters, we want q to be negative 2 meters. Right? So if that's the case, the thin lens equation can be used, and we can say, look, f has to equal q, since 1 over p is essentially 0, so we should have a focal length that is negative your far point. So long story made short, if you want to do a quick correction for a myopic eye, determine what your far point is for your eye, and you can have different far points for left eye, right eye. Once you determine the far point of your eye without any prescription lenses, then go and to the lens maker's equation, right? Grind yourself a lens with a negative lens with a focal length that's negative that far point, and you should see okay. Now, this is, believe me, optometrists do more than just that. Okay, they do a much more in detail analysis than I just did. But this is a quick way to do a quick prescription for your lens. Now, I will mention that optometrists, speaking of them, they like to use something called the lens power. So if you look down here, the lens power, LP, is defined to be the reciprocal focal length. They like to work with reciprocals. I think that's because the thin lens equation is written, right, as the sum of reciprocals. 1 over p plus 1 over q is 1 over f. So they call 1 over f the lens power. In fact, I know 1 over p is called something else by optometrists. I forget what it is. And 1 over q is called something else. So they remember the thin lens equation as something plus something is lens power. So if you take the focal length, the reciprocal of it, you will get the lens power. Now, if you put the focal length in meters, so that your lens power is in reciprocal meters, that is what optometrists call a diopter. So the prescription that is written for your lens will be written in diopters. If you've ever looked at your prescription and said, what is that? That's going to be diopters. Okay, so to fix myopia, just make the focal length minus the far point of the unhealthy or myopic eye. Now, what about if you have hyperopia? Which, again, bad term, I think, is called farsightedness. What hyperopia means is you can't see things well that are close to you. Okay, and remember, the healthy near point is 25 centimeters. So if you have hyperopia, you're going to have a near point, an unhealthy near point, that's greater than 25 centimeters. The classic example, right, is everybody is going at some point going to need reading glasses because everybody is going to have hyperopia. And what happens there is, remember, as you bring an object closer to your eye, you have to have a shorter focal length in the cornea lens system. That means the eye lens has to be squished to be really curved. Well, as we age, that lens gets less pliable. So the ciliary muscle is trying to squash it to make it more curved, but it just can't. So that's, you might see your parents or your grandparents needing reading glasses, and without the reading glasses, they have to put the book or iPad farther from their eyes, right? Okay, so what's the solution there? Well, this really is, all you need is a magnifying glass, okay? If I go to the ray trace, again, let me go back to our ray trace. Let me go to the, there it is, the magnifier. Here's what happens, right? Here's the object right here. Now, we would like that object when it's at the healthy near point. So in other words, if I had a healthy eye and I'm going to read something, I'll put it at my near point, let's say. Now, I really may not, but let's just suppose I do. So if I put it at my near point, I can read it just fine. So with the hyperopic eye, what we want to do is when you have that iPad or book at a P of 25 centimeters, we want the image to be formed at your unhealthy near point, right? So when the object is at 25 centimeters from the lens, we want its virtual image to be at whatever the near point is for the unhealthy eye. So the way we will do our amateur optometry work for this condition is, we will say, okay, if we have hyperopia, so we'll still use the thin lens equation, but what we'll do is we're going to set P to 25 centimeters. So when the object is placed 25 centimeters from your eye, we want the image, the virtual image, to be formed at minus, because Q is negative, it's a virtual image formed on the left side of the lens, negative the near point of the eye. So maybe, for instance, the near point of your eye is 40 centimeters instead of 25. So you would want Q to be negative 40 centimeters. And then you can just use the thin lens equation. But we're going to put P always as positive 25 centimeters. And here you're going to have minus the near point. And then you can find out what F is. Boop. And just like with the myopia, you can define the lens power, as you see right here in the summary notes, right? So you can take 1 over that and express that lens power in diopters as so many positive diopters, okay? All right, I'm sorry for the length of this video. I may have babbled on too much, but if you have any questions about this quick vision correction, just let me know, okay? And you have to do something similar to this. I say similar, and you'll see what I mean when you go to do the computer problem, volume 5, number 2, thin lenses. But I'll say more about that in class, okay, or in an email. Okay, that's it. Goodbye.